July 22nd, 2023, 11:47 p.m. Korean time. A preprint paper appears on Archive, the physics community's draft server. Two researchers from Korea University claim they've created a material called LK-99, room temperature superconductor, ambient pressure, made from lead, copper, phosphorus, and oxygen. Within 24 hours, the physics internet explodes. If true, this changes everything. Perfect electrical conductivity at room temperature means zero-loss power transmission across continents, magnetic levitation without cryogenics, fusion reactors that actually work, quantum computers you can build in a garage, the energy crisis solved, climate change manageable, technology leaps forward decades. For 3 weeks, it felt like the future had arrived early. And then, it wasn't. Replication attempts failed. Measurements were questioned. The hype imploded faster than it built. By mid-August, LK-99 was declared dead. A mistake. An embarrassment. The internet moved on. But the scientists didn't. Because hidden in the wreckage of LK-99 was something more important than a miracle material. A roadmap. A lesson. And evidence that room temperature superconductors aren't impossible. Just harder than we hoped. This is the real story. The one nobody told after the hype died. July 22nd, 2023. The paper is titled, "The First Room Temperature Ambient Pressure Superconductor." Authors, Suk-bae Lee and Ji-Hun Kim from Korea University's Quantum Energy Research Center. The claim, LK-99, named after the lead researcher's initials, exhibits zero electrical resistance and the Meissner effect at temperatures up to 127 degrees Celsius, 400 Kelvin. Made from lanackite, lead apatite with copper-doped phosphate, simple synthesis, common materials, room temperature. Too good to be true? The internet thought maybe not. Context matters. Superconductors had been slowly creeping toward higher temperatures for decades. 1911. Mercury superconducts at 4 Kelvin, mere absolute zero. 1986. Copper oxide ceramics at 35 Kelvin, Nobel Prize. 2015. Hydrogen sulfide under pressure at 203 Kelvin, minus 70 degrees Celsius. 2020. Carbonaceous sulfur hydride at 288 Kelvin, 15 degrees Celsius, but requiring 267 gigapascals of pressure. The trend was clear. Higher temperatures were possible, but they required crushing pressures, millions of atmospheres. Impractical. LK-99 claimed room temperature and ambient pressure. If true, it shattered the ceiling. Then came the video, a small, dark sample of LK-99. A magnet placed nearby. The sample lifts slightly. One corner rises off the surface. Partial levitation. Captured on phone video. Posted to YouTube. This wasn't just data. It was visible magic. The Meissner effect. Superconductors expel magnetic fields, causing levitation. Everyone had seen the classic demo. A magnet floating above a superconductor cooled by liquid nitrogen. But this was room temperature. The internet went nuclear. Within 48 hours, replication attempts began worldwide. Chinese labs synthesized LK-99 and posted results online. Some claimed partial success. US national labs ran tests. European research groups tried to replicate. And then, the amateurs joined in. DIY scientists ordered materials on Amazon, set up synthesis in home labs, posted live streams of attempts. Twitter became a real-time global laboratory. Every failed attempt, every ambiguous result, every theory, shared instantly. Communities formed overnight. r/LK-99. Discord servers analyzing data. Collective intelligence trying to crack the synthesis. This was science in the age of social media. Chaotic, rapid, democratic, messy. For about 10 days, the hope held. Semiconductor stocks dropped. If superconductors are easy, chips change. Energy company stocks fluctuated wildly. Copper futures spiked. LK-99 uses copper. Articles appeared. Our room temperature superconductors will change everything. Tech futurists speculated on timelines. Some claimed we were witnessing a paradigm shift in real time. The Nobel Prize Committee was surely watching. But then the skeptics dug deeper. Replication attempts consistently failed to show zero resistance. Measurements were ambiguous. The levitation video, explainable by other phenomena. Maybe it wasn't superconductivity. Maybe it was ferromagnetism, normal magnetic attraction causing the levitation. Critical papers appeared on arXiv. We synthesized LK-99. It's not a superconductor. The community started questioning the original data, measurement techniques, purity of samples. By early August, the consensus was forming. LK-99 doesn't work. So what actually happened? Post-mortem analyses revealed several issues. 1. Material purity. LK-99 is difficult to synthesize cleanly. Samples contained impurities, copper sulfide phases that are diamagnetic, weakly repelled by magnets. The levitation was likely copper sulfide impurities exhibiting weak diamagnetism, not the Meissner effect. 2. Measurement errors. Resistance measurements are delicate. Contact resistance, thermal effects, measurement noise, all can mimic superconductivity in sloppy experiments. 3. Sample variability. Even the original researchers couldn't reliably reproduce their own results. Red flag. The original team stood by their claims, but with growing uncertainty. Internal disputes emerged. One co-author distanced himself from the paper. Patent applications were filed hastily, another red flag. Subsequent attempts by the original team to clarify or improve results were unsuccessful. By September, even sympathetic researchers concluded LK-99, as claimed, does not superconduct at room temperature. But here's the key. The system worked exactly as designed. Bold claim appears, global community tests it. Evidence doesn't support claim. Consensus forms. All in about 6 weeks. Contrast this with historical mistakes. Cold fusion in 1989 took years to fully debunk. Faster-than-light neutrinos in 2011 took months. LK-99 was resolved in weeks because of open preprints, social media coordination, and rapid replication attempts worldwide. Science self-corrected. Publicly. Messily. But effectively. And in that process, we learned something more valuable than a miracle material. We learned what we're still getting wrong about superconductors, and what might actually work. Let's step back. What is a superconductor? Normal conductors, copper, aluminum, have electrical resistance. Electrons scatter off atoms, generating heat. energy is lost. Superconductors have zero resistance. Electrons pair up into Cooper pairs and move through the material without scattering. Once a current starts in a superconducting loop, it flows forever. No power source needed, no energy loss. Scientists have measured supercurrent lasting years without decay. The second property, the Meissner effect. Superconductors don't just exclude magnetic fields, they actively expel them. Place a superconductor in a magnetic field, cool it below its critical temperature, and the field is pushed out. This causes levitation. The expelled magnetic field creates a repulsive force. Magnets float above superconductors. This is quantum mechanics manifest. Macroscopic quantum coherence visible to the naked eye. So why don't we have them everywhere? Conventional superconductors, explained by BCS theory, require extremely cold temperatures. Liquid helium cold, 4 Kelvin, minus 269 degrees Celsius. Maintaining those temperatures requires liquid helium, expensive, scarce, massive insulation systems, constant energy input for cooling. The energy you save from zero resistance is partly offset by refrigeration costs. This is why superconductors are only used where performance justifies cost. MRI machines, particle accelerators, some experimental fusion reactors. Room temperature superconductors would eliminate refrigeration costs. Change the economics completely. So what actually works, even if impractically? The current record holders. Hydrogen-rich compounds under extreme pressure. 2020. Carbonaceous sulfur hydride superconducts at 288 Kelvin, 15 degrees Celsius. Warmer than your refrigerator. The catch? 267 gigapascals of pressure. That's 2.6 million times atmospheric pressure. Achieved only in diamond anvil cells, tiny samples crushed between diamonds. Sample size, microscopic. Impractical for any application. But it proves something crucial. Room temperature superconductivity is physically possible. Theory suggests hydrogen-rich materials are promising because light hydrogen atoms vibrate at high frequencies. High-frequency vibrations, phonons, can mediate stronger electron pairing. Stronger pairing equals higher critical temperatures. The problem: hydrogen wants to escape. Holding it in solid form requires immense pressure. Researchers are searching for materials that chemically stabilize hydrogen at lower pressures, or even ambient pressure. That's the Holy Grail. Meanwhile, another class, Cuprates, copper oxide superconductors discovered in 1986. They hold the record for superconductivity at ambient pressure, 138 Kelvin, minus 135 degrees Celsius. Still cold, but reachable with liquid nitrogen, vastly cheaper than helium. The mystery? We still don't fully understand how they work. They don't fit BCS theory. The mechanism is unconventional, possibly related to quantum spin interactions or exotic pairing. Understanding cuprates might unlock design principles for even higher temperature superconductors. And the search continues. Nitrogen-doped lutetium hydride, 2023. Claimed near room temperature superconductivity at high pressure. Still being verified. Nickelate superconductors, 2019 to present. Similar structure to cuprates. Might reach higher temperatures. Organic superconductors, ongoing. Carbon-based materials with potential for flexibility and easier synthesis. Each candidate is tested rigorously. Most fail. Some show promise. The hunt continues. Here's the embarrassing truth. We don't have a reliable theory for predicting high-temperature superconductors. BCS theory works for conventional superconductors, but for cuprates, hydrogen compounds, we're partially guessing. The discovery process is semi-empirical. Try materials, measure properties, reverse engineer the theory. It's like discovering fire without understanding combustion. It works, but you can't optimize it. Modern approaches use machine learning to screen millions of candidate materials computationally. But without good theory, the search space is enormous. Even when you find a promising material, making it is brutal. Many high-temperature superconductors require precise atomic arrangements, exact stoichiometry, elemental ratios, specific crystal phases, ultra-pure starting materials. LK-99's failure partly stemmed from synthesis difficulty. Small impurities or structural defects kill superconductivity. This is why initial discoveries often can't be replicated. Synthesis is as much art as science. And then there's the hype problem. Room temperature superconductors have been just around the corner for decades. 1989. Cold fusion. Turned out to be wrong. 2000. Magnesium diboride. Promising, but only 39 Kelvin. 2018. Lanthanum hydride under pressure. Real, but impractical. 2023. LK-99. Not real. The pattern. Initial excitement. Premature announcements. Replication failures. Disappointment. It's science communication's greatest weakness. Uncertainty doesn't trend on social media. Nuance doesn't go viral. But "we solved energy forever" does. So what if we actually had room temperature superconductors? Power transmission. Currently, about 6% of electricity is lost as heat in transmission lines. In the US alone, that's 200 billion kilowatt-hours per year, $20 billion worth. Superconducting power lines would eliminate transmission losses, allow thinner cables, higher current density, enable ultra-long-distance transmission, solar from deserts, wind from oceans to cities. This enables a truly global, interconnected grid. Renewable energy becomes viable everywhere. Currently requires cryogenic cooling. Room temperature superconductors make it practical. Trains levitating on magnetic tracks, no friction, no wear, speeds over 600 kilometers per hour. Hyperloop becomes economically viable. Urban maglev becomes common. Electric motors. Superconducting motors are far more efficient and powerful. Electric aircraft become feasible. Jets powered by superconducting motors and batteries. Electric cargo ships, long-haul electric trucks, all more practical with superconducting drivetrains. MRI machines currently require liquid helium cooling, costing thousands per year. Room-temp superconductors make MRI machines cheaper to operate, more portable, field hospitals, rural clinics, more powerful, higher field strengths, better images. Medical imaging becomes accessible globally. Particle physics. Accelerators like the LHC use superconducting magnets cooled to 1.9 Kelvin. Room-temp superconductors would slash energy costs, enable larger, more powerful accelerators, make experiments cheaper and more frequent. Quantum computing. Some approaches use superconducting qubits. Room-temp operation would be transformative. Quantum computers without dilution refrigerators. So when will it happen? Honest answer, we don't know. Optimistic scenario, 2030s. A breakthrough material is discovered, synthesis is mastered, Applications begin deployment by 2040. Realistic scenario, 2040s to 2050s. Incremental progress continues. Temperatures creep higher, eventually crossing room temperature with practical synthesis. Pessimistic scenario, never at ambient pressure. Fundamental physics limits prevent it. We're stuck with high-pressure systems or modest temperature gains. Surveys of condensed matter physicists suggest 50 to 60% believe room-temp ambient pressure superconductors are physically possible. But timelines are uncertain. To get there, we need 1. Better theory. Understanding the mechanism behind high-temp superconductivity. This requires advances in quantum many-body physics, one of the hardest problems in science. 2. Better computational tools. AI and quantum simulations to screen materials faster. 3. Better synthesis techniques. Precision manufacturing at the atomic scale. Clean rooms, automated synthesis, real-time characterization. 4. More funding. Superconductor research is chronically underfunded relative to its potential impact. Government labs and universities need sustained support. 5. Patience. Science doesn't run on hype cycles. Breakthroughs take decades. And new researchers, people inspired by moments like LK-99, even if it failed. The LK-99 episode revealed something about modern science. For the first time, a major scientific controversy played out in real time, in public, on social media. Traditionally, science happened in journals, peer review taking months, debates confined to conferences. LK-99 happened on Twitter. Replication attempts on YouTube. Data analysis on Reddit. Positives: rapid error correction, global collaboration, public engagement with real science. Negatives: premature conclusions, misinformation spread, hype overwhelming caution. The future of science is transparent. We need to get better at doing science publicly without sacrificing rigor. And the scientific lessons from LK-99? 1. Replication is everything. Extraordinary claims require extraordinary evidence and independent verification. 2. Material synthesis is hard. Just because a compound exists doesn't mean you can make it reliably. 3. Measurement is subtle. Mistaking diamagnetism for the Meissner effect. Confusing contact resistance for zero resistance. Details matter. 4. Hype is dangerous. Premature announcements set back the field by eroding public trust. But most importantly, failure teaches more than success. Every failed candidate narrows the search space. Every replicated result, even negative, is data. Today, labs around the world continue the search. New candidates are tested every year, some promising, most not, all contributing to understanding. Room temperature superconductors may arrive in 2030, or 2050, or never. But the pursuit itself drives science forward. New materials, new theories, new techniques. And somewhere, maybe in a university lab, maybe in a corporate research center, maybe in someone's garage, someone is synthesizing the next candidate, testing it, measuring it, posting the results online. And maybe, just maybe, this time it'll work. July 2023 feels like a lifetime ago. For 3 weeks, we believed in magic. A purple-black rock that could change civilization overnight. It wasn't magic. It wasn't even superconducting. But the hunger it revealed, the global excitement, the rapid collaboration, the willingness to drop everything and test a bold idea, that was real. And the progress since? Also real. Room temperature superconductors won't arrive as a miracle. They'll arrive as engineering. Decades of work, thousands of failed experiments, incremental understanding. The difference between magic and engineering is time. Magic happens overnight. Engineering happens over decades. Magic is a viral video. Engineering is 10,000 replications that nobody tweets about. Magic is believing a material will save us. Engineering is building the tools to test it. And when room temperature superconductors finally arrive, whether in 2030 or 2060, it won't feel like magic. It'll feel like science. Slow, uncertain, messy, self-correcting, and absolutely worth the wait. This is Cosmic Canvas, where hype meets reality, and reality wins. Until next time, stay skeptical, stay curious, and never stop testing.